Okay, so I just thought about how to start this, and I don't know if you were mostly freshmen or not, but I always get really excited about things which actually work, like planes. There's like a joke, somebody was saying like, people complain about bad food on the way from New York to Los Angeles. Like, you would be flying at 10,000 feet in 5 hours, which used to be a half-year journey. It's magic, right? You have to think about it. Phones, you guys use these phones, right? How come that I can kind of push a button and there's like somebody that can connect to everything? It's just like, I don't know how these things, do you know how these things work? How it is magic in my mind. Immunizations, we have been through this the last couple of years. Somebody figured it out, it works. I didn't get sick. Just all this, you can go and get your back clean when your back blows up. You're too young for that, I think, at this point, but I just had some of this summer. It's amazing what people can do. I remember, and this is ages me, right? My father would call to his mom on a phone which was on a wall. It was yelling so much, I cannot yell here very much, so that she can hear, which was 2 hours away from the car. And now I go to Zoom meeting and I speak to a guy who's in Germany, who's in Canada, who's in India at the same time. It all works. Do you know how this works? I don't. This is kind of stuff which we take for granted. We're not dying at age 30 from typhoid. That's pretty cool that we understand this. All this is because we have science, right? You are coming in as freshmen to a place where you can understand, be kind of invited into this world, which works, which produces something which makes our lives better. You may choose different parts of this university. Somebody likes engineering, somebody likes microbiology, but you will understand how this thing works. So if somebody comes with immunization and tells me this is what my process was, this is how I thought about this, this is I use science, I'm like, okay, I get it, because I know how I work in science, and that helps me to not understand the details how the magic works, but understand it's not magic. So let me try to talk about mathematical models, which is what I work on, and kind of talk about how biology is different from physics in terms of modeling. So first I start with physics, right? There's a hurricane somewhere in the Pacific, or sort of Atlantic, which is maybe going to New York. We can predict where it goes, right? There's all these lines which you see on TV going forward. Right? Well, somebody has to do some computations and figure what it is, right? And it works, not 2 weeks ahead, but it works sometime. We can predict scarily effectively. 10, 15 years ago, you were probably not paying attention to this, but there are predictions of what's happening right now in terms of polar weather, very hot, changing climate around the world, as a consequence of driving to a mailbox to check mail. So these things we can do, and all of this is based on physical laws. I want to contrast that with biology. If you do physics, and I'm not probably doing something new here, you have some real world, things are moving. There's planets is the simple system, but and then you have some mathematical description of this, which I'll try to introduce to you, even though you probably did not have differential equations yet. Did you have differential equations yet? Some of you do, some of you did not. Okay. Let me describe how that works. Right? So instead of having a planet of mass, this and this and this, you have an x. X is a description of where the planet is sitting in three-dimensional space, and as a function of time, it's going to move. That movement is my unknown. So not my unknown is 5 or 7, my unknown is a function of time. There are parameters. Again, I'm trying to describe these easy things because I'll talk about biology a little later. These are masses of these objects. And if I say mast, you know what it is. You can go like, okay, I understand mast. I know how to measure it. I can weigh things. Right? I mean, it is very clear how the parameter correspond to our everyday intuition and how we measure them. And then there are some functions which connect these two. Right? And so this is Newton's law for gravitation. But that form is known because that's a physical law. Then you basically solve this problem, whatever the solution means, and you figure out what happens in the future. That's the basic outline of how we do hurricanes and the world. In biology, you also need to predict things, right? You need to predict state of epidemics, what happens next year, the year after, or 2 weeks ahead. People do this. They go and say, oh, we don't like malaria in Florida, which is coming in. One way to do that is to go to the Isthmus of Panama, introduce sterile male mosquitoes, which they will breed, and you can predict based on how many of those mosquitoes are in there, if they will control the population. The population will die down because they will not have progeny. New drugs, will they work? Will they not work? This is very closely to us, right? What about China? If you have 9 to 10,000 feet, they're not doing very well. Will they survive? All this stuff is in biology, and we like to also predict what happens in the future. These are very complex systems which we model. So how do you do modeling of biological systems? Here we do not have Newton's law. So kind of a very basic idea here, it's kind of descriptive model where I make compartments. Compartments are just a group, right? So here's a very simple, I'm going to model for you how zebras and lions interact. Okay? So I have a compartment of zebras, compartment of lions. So the number of Z of t will be in time what the zebras are. I can do density, I can do numbers in Serengeti, I can do whatever units I use. L is lions. And then how do I model that interaction? Well, I know this. Lions eat zebras. So that means that if I have more zebras now, in the future, there's more lions, because lions will eat zebras and have a lot of kids, and they'll be like, oh, very happy and fat. On the other hand, if I have more lions, zebras are not happy because they're being eaten. So we have these basic, very simple facts. And so here's my kind of very simple differential equation which I try to explain. There are some parameters again, right? The parameters are the numbers A, B, C, and D. And the first equation says, okay, so what happens to zebras? You get the Z dot, for those who know, this is a derivative, right? So positive means zebras go up, negative zebras go down. If I have no lions, if lions are 0, then zebras are happily increasing. Right? And then they increase proportionally to zebras. They just multiply. That's my simple assumption. But if I have lions, then this minus says zebras and lions are not good for zebras. It's a negative. Okay? On the other hand, the plus here says lions and zebras make more lions. Lions go up. So it's a very simple, like this up and down type of thing. Right? And I do not know if this is the right form of the equation. Should I have this squared? Should I have a sine function? Should I have a tangent function? How that really works? There's no Newton's law. But based on this kind of stuff, you can do, for instance, the epidemics modeling. So I'll try to go through this. Yeah. This actually works and worked for a couple of years ago. We did quite well what will happen to the pandemic. So I divide humans into 3 categories. Right? This is like zebras and lions. I have susceptible, people who are not sick, healthy. Infectious, they're sick and they transmit virus. And recovered is, okay, they already have had disease, they're not infectious, and most likely they cannot be infected again for some time at least. So sometimes this question mark does not exist. There's some diseases which you are immune for whole life, but at some point, some rate, you're coming back to the susceptible. state, maybe after 2 weeks, maybe after a year, maybe after 10 years, depending on the disease. So this is kind of a basic thing. And then the arrow, which goes to susceptible, depends on whether I'm going to look at the long-term behavior of people getting born and coming in from abroad, or I'm looking at maybe a year or a half, basically my whole population is steady, which is simpler. Then there is no influx. 1927. Okay. Now I have to start working about how things move between categories, like zebras and lions. So how do you become infectious? Well, you meet somebody who is sick, and they give you a bug. That's very simple. So that's this term. So we go, okay, so how does this happen? Well, susceptible and infectious meet. The likelihood of that meeting increases where there's more susceptible, more infectious. So this is the product is the right term, which gives me a bigger number if I have more of each category. The beta is some kind of like a rate of how likely that is to happen. If I have a contact, you get sick. It's not 100% happens, so there's some percentages that depend on the disease a lot. Now, here the assumption which I'm making, which is not good in general, is that this SI term kind of assumes that everybody talks to everybody else. My chance of meeting, if I'm sick and meeting a susceptible person, I can meet any person in the United States, including like obviously stupid, right? That's not happening because people are not mixing nationalization. That's an assumption to make and see how far I can go. This is valid perhaps at MSU or at classroom. And it's not a number. How long it takes to recover, you can measure in days. And so this is kind of a decay rate. There's a rate at which infectious people recover. And the rate gamma is this. So if gamma, if more days, it's a smaller number. That's what it is. And then you compute, you have heard this before, something called the R0, which is the basic pathogen reproduction number. And it's something which, there's a description of this, so let's think about this for a second. It says an average number of infections the infected person gets. Right? So if I'm sick, and I'm sick for 2 weeks, I can give the disease to K number of people. Now that's an average over everybody. So somebody starts coughing, sits home, and never talks to anybody, doesn't give anybody. Somebody else is like, oh, I'm okay, I can go to a party, and here's 100 people I'm going to breathe on and give this disease to 20. This is over the entire time I'm sick. If this is bigger than 1, so the sick person gives disease to more than 1 person, then clearly the epidemic is growing. Because you go from 1 to 2 to 4 to 8, right? You go like this. If it's less than 1, going out. So the question is, what is that number? So you can write this extremely simple differential equation. What I'm trying, this is a description of what the susceptible are going away and become sick with this rate. Sick become recovered this way. It's just 2 numbers in some sense. The R0 initial conditions, that's just how do I start? I start usually the epidemics where almost everybody, this N is the population, it's the ultimate. Almost everybody is susceptible, nobody gets a disease. I drop 1 sick person who comes on a plane. So the I is very, very small. Now you want to see what happens. And here's kind of that model, that simple thing what you see is these kind of curves. What you see is time, and the 4 curves, or 3 or whatever how many I have, depends on the R0. So the R0 is 3.7, again, average number of people a person who is sick, gets the sickness to 2, 1.4, 1.2. So 1.2 is, it's also looking like this. It's very small. Right? This is very fast. This is kind of like how many percentage of the population gets infected? Almost 37% in a very short time. Ignore the days, this is just the times. You have seen these curves, right? The rise and decline. It just comes from this tiny model, which is stupid. People don't mix that well, right? But even that gives you a good estimate of what that's happening. So now the question is like, okay, how do I lower the R0? Right? Because obviously, this was the pandemic question. Like these things will happen. What I don't want is 40% because grocery is about to close and I don't have enough hospital beds. If I can make it into the green, I'll be fine. So how do I lower the R0 was the game of the day. And so what's the R0? Let me concentrate on the second part. You can compute that from that simple equation. Tau is a transmission rate. That means if I meet somebody, how likely he's going to get sick. So if I am susceptible and infectious, how likely the contact results in disease. You can lower that by, so I want to lower tau, I want to lower the whole thing. So lower either this or this, or raise down, rise down. So if I lower tau, that's why we do all this stuff, right? Number of effective contacts, how many people you meet on average. If you stay home, you don't give it to anybody, right? So one way to impose or lower the N, average number of contacts per person, is just social distancing. So, 1/gamma is the time you spend being infectious. If you are 3 weeks infectious, right, the R0 is bigger because you have a lot more likelihood to meet more people and you have somebody. How do I make that 1/gamma smaller? Try to test the quarantine early, all this stuff, antiviral medications, vaccinations, all these things work. So this is how you do that. You kind of get an insight and you say, okay, let me try to work on all these areas. There's some problems with these models, obviously, obvious problems. How do you measure these in real time? I have just heard 2 weeks ago at the conference a very interesting talk that people respond to TV after some delay. So they actually explain why there's a double peak for Omicron. There's a double peak in almost every nation. Because people go like, oh, things are over. Let me start going to out, right? And then those contacts raise a second. There's a delay in how fast people react to news. So usually these insider models are actually better after epidemics when we can fit the models. They fit perfectly. But the middle of it is not so great. Okay? So that's kind of a simple system, right? Simple biological system in some sense. I'm interested in working on a more complex system. What is a complex system? It has much more interactive parts than there's multiple ways how outcome, multiple things. Try to get a red dot here. There's a red dot in terms of multiple places. There's interactions between different factors, and it's hard to discern which one actually worked. Feedback is the word which uses in control theory. There are loops, right? If this changes, I influence myself. That's very difficult to handle. Like this, it's direct feedback. Or much longer feedback. How much time do I have? I'll just think here. So I'm supposed to talk about 10 more minutes? Where's the main person?
You can go like up to an hour.
Well, I have another talk at 3. So.
At 3? Okay.
No. Okay, good. So let me just give you some examples of complex systems. Not necessarily work on all this, but so now I'm kind of in biology in more complex systems than this. Anybody flew here? You guys flew. I know you flew internationally. I came from Tokyo a couple of weeks ago. Why do we do this? Why do we have this? What's a jet lag? Everybody knows?
It's like your body's just accustomed to going to bed and waking up at a certain time.
Yes. But it's more than actually just being like accustomed. There is actually evidence that all our body parts work. Right? I mean, if you are not eating during the day for 8 hours, you'll be starving by eating. At night, you go like, yeah, you eat. at 7 at night, it's 7 in the morning, it's 12 hours. Nobody, I mean, it's not like you start, because your liver, your stomach is like, okay, I know this is the time for me to shut off. You don't work. There's immune system is also has its peaks and troughs. Actually, I think that it's best in the morning for some reason. I don't know if this is because people woke up in a cave and had to go out and fight bears. I'm not suicides. So there are all these little clocks, and the clocks work in all parts of our body, in liver, in stomach, and they are all synchronized by I forgot the name. This is a big word here. Okay? It's a little piece of a bunch of cells in our brain which synchronize all this stuff. And also that synchronizes the natural light. That's why when you go to Europe or someplace, you don't be outside, you know, it's midnight, so that your body resets. Nobody quite knows how this works. Right? But this is kind of like one of those clocks. You can look at coordination. So if you want to do something fancy, jumping on your bike or jumping on the here, sleep, blood pressure, probably likely problem. So we know how these things are synchronized. So there's a big clock, genetic clock, which again is a result of adaptation to 24 hours. Every single, every animal on Earth who has a way to detect light has this, from like cyanobacteria to everybody. Again, what's causing it is a periodic gene expression inside the cells. Other clocks. So here's another clock, which I'm going to show you some pictures of. This is time in hours. Yellow is high, blue is low. And every single line is a gene expression. So if I go from here, you go like low, high, and at different phases. Like this guy's high before that guy. This is the data from 6,000 genes, I think. And what this is the Plasmodium falciparum. Do you know what it is?
Malaria?
Exactly. One of the 5 malaria strains. The most common one. This is malaria. Malaria is a parasite which infects red blood cells in our body and has this very strange behavior once it gets to the red blood cells. Every 48 hours, all these little bugs in 10,000, 100,000 little red blood cells goes like and burst and basically destroy the red blood cells and infect a new batch of red blood cells. At that moment, when you have 10 million of these bugs in your blood, your body goes berserk and obviously start having huge fevers, and this is the periodic fever which is actually detrimental to humans and fries brains of kids and stuff. It's one of the biggest diseases we have on Earth. Army is very interesting because anytime you get 30 degrees off the equator, they get this. So there's 3 of them cause malaria. It will be very interesting to know how to disrupt this clock. There's a clock in these guys. If you know how to disrupt them, and some red blood cells go in the morning, burst in the morning, and some in the afternoon, your immune system will take care of it. Probably. Nobody knows whether that's the case or not because we haven't tried that. But they're overwhelmed when all these things synchronously burst out. So it'll be very interesting to understand who drives this quakes. Cell cycle, not clocks. There's a theme here, a periodic behavior. This is what biologists dump on mathematicians and say, oh, here is what we know. We know how the genes work. This is how they're connected. Tell us what it does. This is complex system. So this is the cell cycle divide. It decides when the cell divides in between. Most of the human cells do not divide regularly, only when needed, only when you get injured, right? Because you want to control that. If it's uncontrolled, it leads to cancer. It's a process which you always listen to other genes. You need to divide. You talk to other cells around you. Is there a space? it's a very, very complex process which not everybody, nobody understands. So the question of how do you model these complex, and that's what I'm interested in, gene regulatory networks. It's a good question how do you actually start? Because you have these, complex things which biologists need. But it seems it's harder than physics in the following sense. There is no precise law. So I don't know how to write that nonlinearity in the system, how things interact with each other. And there's a lot of choices. Parameters were the A's and B's and C's, which I showed you, or mass for the celestial stuff. You can measure mass. But here, there's a kind of a number kappa. Like, well, what's kappa? Well, kind of like if you do more of this, you do more of that. It's kind of a threshold. Like, how do I measure this? They go, well, you first fix the model, and we fit the model to data, and it's very difficult to get like first principle parameters. So let me kind of have a few more slides. So that's the challenge for in biology. How do I actually, what's the meaning from model? Here's a slide in history of mathematics. Perfect. And it kind of leads to what the challenge is right now. So again, in early physics, I don't know if you know these names, Newton, Leibniz, Laplace, all these people, they're trying to find precise models of the laws, right? And that's what you learn in physics every day. What is the law, how the electromagnetics work, and all this stuff, right? And then the goal is to say, okay, I want to solve that. I want to solve X, Y. I want to solve X of t, Y of t as a function of time. And so I can precisely draw that and know where I am in terms of planets. Poincaré, this is the late 19th century, realized that's not possible. And we know now that if I have three body problems, not just the moon, not just Earth and Sun, but Earth, Sun, and Moon, to actually solve those precisely is impossible in terms of sines and cosines and functions. You can solve it numerically make numerical errors. So if we send a something to Jupiter, what we do, we kind of compute out on a supercomputer a month out. And then after a month, we just kind of like phone and go like, okay, where are you? Well, I'm here. Well, you're not quite where we thought you would be. You're probably 10 miles away. Let me just do a little burst and put you back home. Okay? That's the only way how we can do it because we cannot compute precisely for all time forward. We can compute for some time and we can error range. And so Poincaré realized that this kind of trying to find these kind of solutions, exact solutions to these precise models, is futile. We rather start doing things where we qualitatively conclude something. Things go to periodic orbit, things go to a fixed point, things will be two fixed points, will be two states which just state. That's sufficient in many, many instances. You don't need that first thing. And this is the classes you take these things. Because if you go in a differential equation, which is left, you're going to learn how to solve differential equations. You probably have done it already. But that's not how you can deal with nonlinear problems. If you want to know that, you have to go to 454 dynamics class, which is for the biological system, we have to go a step forward because we have we don't have precise models. We have these qualitative models. This goes here, how much, but I don't know exactly what the model is. And I have to figure out how to do that, how to get solutions to these kind of models. So that's what we're working on. So kind of the most mathematical part I'm working on with my group is kind of develop these methodologies for the gene regulatory network type of stuff, where you can actually scan through all the parameters, all nonlinearities, to find kind of a rough dynamical behavior. You know, do I have a bistability? Do I have periodic behavior? Do I have a fixed point for a gene regulatory network? I also work, and this is kind of a different story. This is more biological, more close to the ground. Ross Carlson is a guy in chemical biology engineering. He's interested in consortia and microbes which are growing together and they feed each other, and there are all different ways how they interact and how you can affect that, how you can actually make them cooperate, how you make them not cheat on each other, that kind of questions. So I try to do work with them to do some of the processes. And then I also have close collaboration with Stephanie Nicola from the same department. It's a little different can of worms. She's interested in detecting microRNAs, which are very, very small, 20, 30 base pairs pieces, which are floating around the body often. They often can be indicative of disease, which is happening, but they're very, very difficult to detect because they're tiny. So one way to detect them is to do PCR, polymerase chain reaction. PCR. It's something like this. It's actually, that's the technology which came out of Yellowstone. You take a DNA or some DNA is double stranded. You heat it up, and you put into the solution a piece of it which is kind of complementary to it, which is matching first 10 base pairs, let's say, of the strand. You put a bunch of them in there. And you put a bunch of polymerases, which are the copy machines of the DNA. And so you heat it up, these things kind of dissolve. Now you cool it down, so now you have the little piece bind on it, and the polymerase finishes off. The polymerase, when it sees one single strand with a little primer, it finishes off, makes it DNA. So you separate, primers bind, you cool, polymerase make 2 copies. Heat, cool, heat, cool, heat, cool. You double your DNA. After you get 10 to the 6 pieces of it, now you can see it. Now you can produce the dye and stuff. You can see that machine costs about $1 million. Maybe that was less. Now it's less. But it's a very, very special technology because you have to very carefully heat things up and cool it down precisely in a way that you don't destroy the other things. The key part to it is that the machine which copies it must be resistant to the heating. Everything which you heat up, proteins disintegrate. That's why you can eat cooked. Right? So you have to have a polymerase which persists in that heat. And that's the polymerase which comes from Yellowstone, from the bugs in the hot springs. Okay. So the issue with that is that it requires a very complex machine. If you want to apply this technology to, say, detection of malaria in Thailand, backcountry, there is no PCR machine anywhere in 2,000 miles. But that's where the malaria is, that's where the bugs, that's where the emergent pathogens are. So there are ways how you can make a so-called temperature-independent multiplication things. They became kind of weird. Isothermal is the word. Isothermal multiplication. They behave a little weirdly, so we're trying to figure out mathematically why they do. All right, here's my lab. If you want to, there's undergraduate students. Bree was a postdoc with me. Now she is a faculty member in mathematics. PhD students. So if you are ever interested in any of this, just let me know. Okay? And I'm open for questions. Yes?
Could you elaborate more on the modeling you're doing for the UDAR reaction?
Whoa, do you even know the name?
Yeah.
Okay. So the UDAR has this kind of double, it's a double, so UDAR is a name for this isothermal assay. And what happens is that let me try to explain that. So there's multiple players in there, right? We have something which I call a trigger, which is the thing which I want to detect, or something which I want to find, I want to amplify. I have a piece of DNA which has that kind of copy of the binding site. You can copy that thing that's binding to have. When that happens, polymerase comes and fills it in. What the other part is the same copy of it. Kind of have the same, this is A, and this is also A. So now it kind of fills it in, and in the middle there's a restriction site where the restriction enzyme comes and cuts it open. So now I actually get 2 pieces of it. So it's kind of the same idea from 1 to 2. what Stephanie and I, or Stephanie, we came up with a couple of years ago, the big problem with this is that there's something which is called false positives, where this thing is just hanging out there, and there's no trigger to actually complement the 20 base pairs. But they're just random pieces floating around, and they come in and bind 1 or 2 or 3. When 2 or 3 happens, the polymerase goes like, oh yeah, let me make a copy of it. And also when you make a copy, now you have actually a real copy because the other end is the real piece of it. So we didn't have any trigger, now I have a trigger. And now I have a trigger, oh, and things just go and have a chain reaction. So usually that happens alone. It takes a longer time to have the random assembly. So if I have a comparison between the real thing at concentration 10 to the -5, 10 to the -7, 10 to the -8, nothing, then this happens in 5 minutes, 7 minutes, 8 minutes, 10 minutes. So hopefully, if you say, okay, after 10 minutes, after 8 minutes, I'm done, you can detect the real one, but not the other one. The problem is that day to day, there's a variability, how you mix the things up, how much it's very sensitive to temperature, day, nobody knows why. So one day is 10 minutes, one day is 7 minutes, one day is 5 minutes. So from day to day to day, there's no like a hardcore, like, okay, here's the protocol for Thailand. If you don't see things in 7 minutes, there's nothing in there. Depends. So it'd be really good to have a way to suppress those things. So she did something where she had this string, this thing which is detecting it, and it was binding back, has like a loop in it, right? So it actually binds back to itself and closes it. Now it's much harder to open. If I have the real signal, it does open it. Actually, you need 2 pieces to open it. But if I have the fake signal, it will have much harder to do it. What happens, you have some kind of like, in time, you start to have these kind of big 2 bumps coming up. Nobody knows why the second bump is in there. So what I was doing was, we put together, I had a PhD student which finished maybe 4 years ago. You start having kind of these compartments. It's like, okay, I have the triggers, I have the base pairs, I have things which come off, and I have rates of how fast each thing is going. I just write a set of differential equations, 7 or 8, and try to see parameters if I can find the same kind of curve, and then move them in a way, if I want to control it, how to do it. So that's kind of.
Thank you.
Those 2 detailed.
So when you talk about stuff like the 3-body problem and like really complex systems like that, is it that there's truly no precise mathematical solution that can be calculated, or is it just that to calculate it would require a ridiculous amount of computing power?
So that's a very good question. So all these problems have a solution in terms of there is a curve, right, which solves it. The problem is that that curve does not have when you learn in 274, 275, solving simple equations where the solutions would be sines, cosines, exponentials, polynomials, right? Those are functions which we know. It's a sine is a shortcut, right? If I ask you, give me a sine of 0.3, you have no idea how to do it.
Yeah.
The only functions which actually know how to compute are polynomials. Because if I say 0.3 cubed, you actually go in and multiply and get a number. All the other functions are shortcuts for more complex functions which we can approximate by using Taylor expansion. But the rules just don't give you an option to find a solution as this cosine, sine, arctangent, right, which you can evaluate. So what you can always numerically approximate. But numerical approximation, I don't really want to go to math here, right? But I have a curve which exists. I know it exists. What happens is it changes every single moment. So what you do numerically, you kind of say, oh, I can compute derivative here. That's a tangent line. I do a step. So this is approximation of the real curve, which curves underneath. It's just like this, right? That's the approximation. You do it again, you do it again. The error accumulates. So we can, in bigger computers, I always say, why cannot forecast, weather forecasts for more than 4 days? Think about it, these chaotic systems, very complex systems, have behavior where the nearby solutions diverge in time. So if I measure right now, temperature, pressure, whatever you need from physics, in entire west from us for 10,000 miles. But I'm saying every point of the atmosphere. PD solution has a unique solution forward. You can solve for weather going forward. For 10 days, for 12 days, whatever. The problem is that you have few water balloons, the air balloons which go out there and measure temperature over Seattle, over Oregon, right? So I have these very few data points. And those data points are consistent with many initial conditions. Right? The state of the system could be anything which has temperature pressure in Seattle like this and Oregon like this, but in between, I have no idea. So I really start with a big ball of initial conditions. And then I go forward, and they spread. So within 5 days, in that ball is initial condition which leads to huge thunderstorm. In the same ball, there's initial condition which leads to 95 degrees temperature. And so you go like, eh. Right? So the only way how to be more precise in these things is to measure your initial condition more precisely. And that's not possible. So if you do that, if we spend $10 billion to build more stations, because it's exponentially going like this, you gain 2 days. Is it worth it? Probably not. So these chaotic complex systems have this divergence property. So the fundamental limit, you can always approximate, but there will be no approximation past some point. Or you can always approximate more if you spend more money. It's not worth it. Very good questions. Nice lift. Because I'm leaving for Brown next day, like for a semester-long thing. They asked me to give talks, so I'm going to talk here, and then going to be talking in Apply Math at 3 o'clock. So, plenty of time. If there's more questions.
Oh, no, I was just saying, it's a little over my head, but I understood what you were saying with the weather.
I mean,
I'm not a math person, but it's
But that's a common, right? I mean, that's why people, when they ask about global warming and climate, it is an even more complicated problem. They compute these things forward by dividing Earth into like 50, maybe now it's down to 10 kilometer squares, right? And say, and assign temperature, how much sun is reflected out, all this kind of, to each of these squares, and trying to figure out how they connect to each other. But 10 kilometers, and that's like supercomputers for a while, cranking for years. It's approximate, right? It's not quite correct. So the predictions today we can compute forward 50 years, but afterwards it's just like, and that discovery, the deterministic systems like three-body problems, which are those physical laws. It's like it's right there. You know what it is, but can lead to, again, this is called chaotic behavior. Right? It's not. If I know exactly where I am, I can compute unique solution. But every time I have a little uncertainty of where I am, that thing spreads out, and after some time, you're like someplace. That is fundamental limiting limit to determinism of how far we can predict the future.
So the differential equations you're using for the modeling have like time-dependent functions in them, and like some of them are very simple, but how are you using data to find those functions?
That's a very good question. There are, so the most common way to do that, which is not the best, right, but is that you run a model, right, and you get an expression, and like, for instance, those curves, those exponential curves, what easily can happen, you run a bunch of those curves, you look at the data, and you just move your R0 around until the thing fits exactly. So, so that must have, but usually that's like in the retrospect, that must have been R0, right? Because remember, R0 is a kind of population-wide count. It's not, right? So you kind of fit it by doing that kind of stuff. It is more complicated. So you take a model, you basically pick random parameters, so you have some kind of idea of what parameters are. You run a system, and you compare the data, and you adjust the parameters. that's usually the kind of philosophical problem with that is that if I have a big enough model, there will be many combinations of parameters which fit the same data. So how it's like it's ill. So it's kind of a judgment. And every time we do mathematical model, you simplify, right? There's a simplification going on. So the paradigm which one should do is that you put a model down which is as simple as you can get. If it fits, good. If it doesn't fit, it's even better. Because if it doesn't fit, you're missing something important. And you go like, what can I add to my model? What feature I did not account for? And if I can add that thing and that fits, now and that is important. If I just fit a model, I may be just lucky. So actually that like not fitting and then fitting, you get information. So. All right, thank you guys, very much appreciate it.